Hello everyone, the topic of this week's tutorial is set theory. Let's recap first. We have learned the definition of set, Venn diagram, condition product, and partition. So let's go to the concept of set first. What's a set? A set is a collection of abstract objects. There are two ways to specify a set. Explicit way, we can just enumerate the members, such as 2, 3 is members of a set A, and then there is a implicit way. A is made of X, where X is a prime number. Okay, that's an implicit way. And then we will talk about the membership. We denote X belongs to a set if and only if X is an element or is a member of set S. Okay. For example, 2 is a member of A, so we say 2 belongs to A. 2 belongs to A. And also 3 belongs to A, but 1 or 4 is not belongs to A. And then we will talk about the subset. The subset. We need to know the definition of subset. A set A, we say a set A is a subset of the set B, denoted by A. If and only if every element of A is also an element of B. Okay, we can say for all X, if X belongs to A, then X also belongs to B. So that's the definition of subset. If A is a subset of B, only if and only if for all X, this element X belongs to A, then this X also belongs to B. That's the relationship between A is a subset of B and the predicates. Also, for the empty set, we need to note an empty set or null set is not equal to the set of empty set. Okay, that's a different thing. And how to prove a set equals to another set, such as A equals to B. How to prove this set equality? We start from the definition. For all X, if X belongs to A, then X belongs to B. And also, if any x belongs to B, then this x also belongs to A. So that's the two-direction equality. And then comes to cardinality. The cardinality of S of a set is the number of the elements in this set. Okay. If a set A like this, the cardinality of A is 2. Okay. It denotes the number of elements in this set. Then we come to the important definition. Power set. Okay. What's a power set? A power set P of S is a set of all subsets of S. If A is a subset of S, and then we correct all the A to be a set. So, do we have any information for the power set? Yes. If a set S has n elements, then the power set of S will have 2 to the power of n elements. Okay, and then it comes to Venn diagram. A Venn diagram is used to show or visualize the possible relations among a collection of sets. So, in short, a Venn diagram is used to show the relations between several sets, such as we can have two sets like this, two sets like this, and then two sets like this, right? This means the two sets are disjoint, and then the intersection of set A and B is this part. Okay. And for the third situation is that A is completed inside B. Okay, so this means A and B equals to A. For the Venn diagram, we need to note a set difference and complement. Okay. A minus B. It means what? A difference of A and B is a set containing those elements that are in A but not in B. We use an implicit way to describe this set. Means for X, it belongs to A or in A. And this element is not in B. And then comes to the Cartesian product. the Cartesian product A times B is a set of all ordered pair A, B, where A is in big A. The small b is in set B. Is a mathematical formula to describe this situation is that the Cartesian product is an ordered pair AB, where A is in set A and B is in set B. We can just take an example. If A is 1, 2, and B is x, y, so there is a ordered pairs where A can only be 1 and 2, and B can only be x and y. Okay, so we have 2 times 2, there will be 4 cases, right? So 1 x, 1 y, and then 2x, 2y. Okay, and then we come to the partition. The definition of partition is that we have a universe A, and then we divided A into several parts, and then all the parts A1, A2, AN, all these parts are mutually disjoint. Means AI, A and AJ equals to a empty set. And then we will talk about the second part of set theory, set identities and prove the set identities. First it comes to the set difference. For the set difference, we have sign expressions need to keep in mind. A minus B, it means set difference between A and B is equivalent to the intersection of A and the complement of set B. This means the elements is in A but not in B. Okay, and then we can recall we have an implicit way to describe the set. We have X, and X need to satisfy the it is in A but this element is not in B. And then if we have a complement of the intersection of A and the complement of set B, and then we can just use something like the Demogorgon law to simplify this expression. Okay, we just take the complement as a negation inside. We will have the complement of A and will become an OR operation. It means intersection becomes the union, right? And then we have the complement of set B. It's just like a negation. Two negation will become itself. And then we have learned 3 methods to prove set identities. First, we need to show each set is a subset of the other, and also we can use set identity theorems. And then the same method is using a membership table. We will use questions from the assignment to explain the 3 different methods. And let's all follow the recap, and then we will go through the assignment. For the question 1 of the set theory, we need to deduce the cardinality of a power set of a finite set S with n elements is 2 to the power of n. For this question, we need to recall the definition of the power set. The power set is the set of all the subsets of a finite set S. So a power set S is a set of all the subset of set S. Okay. So the subset can have I elements, right? So these I elements can be chosen from n elements. So we will have n choose I, the number of subsets of I elements. If we sum up all the situations, I can start from 0. It means this set is empty set, right? And also it can have n elements. So if we sum up all the situations, this is a cardinality of the power set of S, right? So the problem will be reduced to the sum. So how to calculate the sum? We start from the binomial theorem. This is just the expansion of 1 plus 1 to the power of n. So that's how we get 2 to the power of n to denote the cardinality of the power set of S. And then for the question 2, when you compute the cardinality using 2 different ways, the counting approach and the binomial theorem approach, we can just use the conclusion from question 1. So if we use the binomial theorem approach, A is 1, 2, 3. It has 3 elements, right? So the cardinality of the power set of A is 2 to the power of 3. Also, if we use the counting approach, it would be empty set, and then we choose 1 element from 1 to 3, right? So we will have 1, 2, 3. If we choose 2 elements out of the 1, 2, 3, we will have 1, 2, 1, 3. and then 2, 3. If we choose 3 elements out of 1, 2, 3, we will have 1, 2, 3. Okay, so we will have 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so we have 8 to denote the cardinality of the power set A. For the question 3, we need to determine the power set of A and B. The power set of A, the power set of A or B. The power set, the Cartesian product of A and B. For this question, we need to calculate the set first. Okay, so for the intersection of set A and B is 2. So the power set of this set would be empty set and itself. Also, A is 1, 2. So the power set of A is firstly empty set, and then only choose 1 element. If we choose 2 elements, after you calculate the power set, we can use formula 2 to the power of n to check what we have got is correct or wrong. So we have 2 elements, right? So the cardinality of the power set should be 2 to the power of 2 is 4. So we will have 4 elements. So 1, 2, 3, 4. So this can make sure you got the correct answer. In the union of set A and B, we got 1, 2, 3. And then we can just use a counting approach to calculate the power set, right? And then we should have 8 elements here. Okay, and then I will show A times C, the Cartesian product. It means what? We have a ordered pair, right? A, B. And then A belongs to set A. And element B is in set B. Okay, so for the problem here, A times B, the Cartesian product, is 1, 2, 1, 3, 2, 2, 2, 3. And then after we calculate the Cartesian product, it's similar to use counting approach to calculate the Cartesian product. It's almost the same. Firstly, we only consider we pick up 1 element out of the 4 elements, and then we choose 2 elements. Firstly, we only care we choose 1 element out of the 4, and then we choose 2 elements out of the 4, and then we choose 3 elements out of 4. and then we choose 4 elements out of 4. Actually, we should have 2 to the power of 4 is 16 elements for the power set of A times B. As for question 2, we need to prove by contradiction that for the 2 sets A and B, A minus B and B minus A intersection is empty. It asks us to prove by contradiction, so we need to assume the results is not empty first. So this means there exists X to satisfy this requirement. Okay. So X is in this set. This means X belongs to A minus B and B minus A at the same time. For the situation X is in A minus B, this means X is inside A, right? And also for the situation X is in B minus A, this also means X belongs to set B. And X is not in set A. It's N here, so we need to satisfy X belongs to A and X doesn't belong to A at the same time. But here it needs to satisfy the situation that X is in A, and here X is not in A, so that's a contradiction. For question 5, we need to prove the statement power set of A equals to power set B is equivalent to A equals to B. It's a 2-direction statement, so we can prove this in 2 directions. So if we have the power set of A equals to power set B, and then we will have A equals to B. And also, if we have set A equals to set B, and then the power set of A equals to power set of B. Okay, so for the first case, if we have power set of A equals to power set of B, this means the subset of single elements should be same for both, right? Which means A is equal to B. But you need to write down, since we have the power set A equals to power set B, and then the power set equals the set of the subset of a set, right? The subset includes a single element situation. So if we have the power set equal, then the subsets of single elements should be the same, which means A equals to B. Okay. And then for the second case, if we have A, set A equals to set B, this implies, of course implies PA equals to power set of B. Of course, right? It's obvious if we have the two identical sets and then the power sets are the same. And then for question 6, if power set of A is a subset of power set of B, this is equal to A is a subset of B. Also, it's a two-direction statement, so we can prove it in this case and then in this case. So firstly, we consider if we have a power set of A is a subset of power set of B, this also means every single element, the subset of single elements, single element in our set of A are also in our set of B. So we can have A is a subset of B. And also, if we have A is a subset of B, first, and then we need to think about the relationship between power set of A and set of B, power set of B. So if we have an element is in power set of A, we need to recall the power set is the set of all the subsets of a set A. So for every element in this power set, it's a subset of A. I know someone may be confused about this. Just recall, the power set is a collection of the subsets of set A. So every element in the power set is a subset of set A. Okay. And then we have A is a subset of B. So we will have X is also a subset of B. So X is in the power set of B. Okay. So we start from here. If we have a X is in the power set of A, and then this element is also in a power set of B. That's the definition of a subset. If we have a for all x if this x is in set A and then x is in B, the definition of the subset is this. This means set A is a subset of B. So when we have this, we can get power set of A is a subset of power set of B. Okay, by using the definition. For question 7, we need to show the empty set is a subset of any set. So for this kind of question, it's something like a definition, right? So we may use the definition to prove this. So we need to recall the definition of a subset. For all x, if x is in A, implies x is also in B. That's the definition of A is a subset of B. Okay. So for this question, we need to show the empty set is a subset of any set. How about we just make A is an empty set and B is a random set, is any set. Okay. So let's look at the left hand side. If A is an empty set and X is in A, for this statement, it's always false. So for the whole conditional statement, it's always true. This means we don't care B is empty or not or anything, since this conditional statement is always true. So the empty set is a subset of any set. For question 8, we need to show when A is not equal to B, now exists X in set A, but it's not in set B. Or X is in set B, but X is not in A. It's obviously the same and it's true. So how to prove that? For an obvious statement, we usually starting from the definition. If A equals to B, according to the definition, is that for all x, if x is in set A and also is in set B, and if this x is in set B, also is in set A. That's the definition of A equals to B. So now we need to consider the situation A is not equal to B. So we can, how about we just take a negation? A negation here. Firstly, for the quantifier, we take a negation, we will have a exist x here, right? And then For a biconditional statement, we have a negation. And then we need to separate the biconditional statement into two conditional statements. And if we take the negation inside, we will have and then we need to change the and to or, right? And the same thing for the second term. And then for a conditional statement, we usually change the form as if we have P implies to Q, and then we will have not P or Q, right? It's the same. Not the first term, it means or the second term. It's similar. How to deal with this? We have not the first term or the second term. And again, we take the negation inside. So we will have X is in A, and then we change it all to and X is not in B. Or X is in B and X is not in A. And then we can compare the conclusion and the requirement. It's the same, right? So that's the right hand side. So this statement is proved. And then something we need to note is that from the first line to the second line, we use the negation of the universal quantifier. Okay, and then we separate a biconditional operator into two statements and use the and to connect the two conditional statements. And then we use the De Morgan law to take the negation inside. After that, we use a conversion theorem to change the conditional statement to the statement. Okay, and the last line is the De Morgan law. Again, we just take the negation inside. For question 9, we need to prove this equality. So for this kind of question, if we start from the left hand side, for any x is in this set, since it's all operator here, it means this element can be in the first set and also can be in the second set. So there are two different cases. If X is in the Cartesian product of A and B, this means X could be X1, X2, where X1 is in set A and X2 is in set B. X1 is in set A and X2 is in set B. According to the definition, if A is a subset of A or C, and X1 is also in A or C, right? So it's similar for the second case. If we have B or D here, and then X2 is also in B or D. How to think, how to reach here is that we always need to make a relationship or just generate a link between the left hand side to the right hand side, right? So if we have this X1 is in A, X2 is in B, it's still a little bit difference between what we have got to the right hand side. So if we have the union of set A and C, and then we can create the link, and also the same thing. So this means X is in A or C times B or D. Since X1 could be in this set and X2 could be in this set. For the case X is in set X is in set, the Cartesian product of C and D is almost the same procedure. So we can have the statement proved. So the question is that, does the equality hold? So first we can just take some example to check the equality hold or not. So if we take A is intervals, okay. But also the intervals starting from -1 to 0. And C is starting from 0 to 1. D is starting from 0 to 1. For all sets are intervals, we can just check the A times B, the Cartesian product A and B, okay? It's this, right? And then we have C and D is and then the right hand side is A or C. A or C is -1 to 1, and also the same thing B or D is -1 to 1. So the right hand side could be -1 to 1 times -1 to 1. We can see the union of these two doesn't equal to the here, such as if the x1 are chosen from -1 to 0, and then x2 chosen from 0 to 1. For this case, is not included in the Cartesian product of A and B or the Cartesian product of C and D. But we denote this as Y, and the union of these two is X. For this case, it's a subset of Y, but X and this set is empty, since if x1 is chosen from -1 to 0, y is chosen from -1 to 0 also, but not chosen from 0 to 1. So the intersection is empty. So the equality doesn't hold necessarily. For question 11, it asks how many subsets of 1 to n are there with an even number of elements. So for the number of subsets of 1 to n, how many subsets are there? Since this has n elements, so the number of subsets will be 2 to the power of n. How to calculate the 2 to the power of n? We can use binomial theorem, right? This is a sum over starting from I equals to 0 and I equals to n. N choose I, right? So I denotes the number of elements, right? Of a subset. So 2 to the power of n is two different situations. If I is odd, if I is even, right? That's a case to calculate the sum of when I is odd, when I is even. Starting from this, and here we need to calculate them separately. But here, we have a plus between all the different I. How to create a minus? Why I recall this is that if we denote the first term as x, the second term is y, and x denotes the number of subsets of odd number. The elements number is odd, and then the second thing is the subsets of the number of subsets of with an even number of elements, right? So we have x plus y equals to 2 to the power of n. What if we have x minus y equals to a constant? We don't know. Actually, we don't know here. So how to create? Then I find if we change the 2 to the power of n is 1 plus 1 to the power of n, right? So how to generate a minus 1? What if we have a 1 minus 1 to the power of n? And then we can get and then this is when I is even, this is when I is odd, and the general term is that I starting from 0 and with n, and then we choose n, choose I here, and then for the symbol is minus 1 to the power of I. So when I is even, the symbol is positive, and then when I is odd, the symbol is negative. So we actually generate y minus x here, right? But y minus x it equals to 0, and then we have x plus y equals to 2 to the power of n. So we will have x equals to y is 2 to the power of n minus 1. So that's how I solve this problem. For question 12, we need to prove 7 times a plus 9b, and where a, b is an integer, it's equivalent to the integer set. How to prove this? Integers as 1, 2, 3, and so on, and 0, minus 1, minus 2, and then we can see the gap is 1, right? So if we can find 1 and times n, can be any n, right? It's n, an integer. So what if we can find 7a1 plus 9b1 equals to 1? Then we can use this expression to express an integer. If a1 is minus 5, b1 is 4, and then this equation holds. What if a equals to 5 minus 5 times n b equals to 4 times n, and then we will have 7 times minus 5 plus 9 times 4. That's n. Okay, n here can represent all integers. So this equality holds. For question 3, we need to prove this set equality. So it's related to the set difference. So we need to recall the definition. A minus b, it's x is in A and x is not in B. It's also the same thing as A and B complement in the intersection of set A and a complement of B. Okay, so we make a connection between the two. So for this question, A minus B or C here, we use B or C to substitute the set B here. We will have A and B or C and then complement. And then we use the Morgan law. We will have a complement of B and complement of C. That's left hand side. Okay, and then for the right hand side, A minus B is A and the complement of B, and A, the intersection of set A and complement of C. And then we expand it, we will have A and A is A. So okay, fine. The intermediate state is the same, so the left hand side equals to the right hand side. For question 14, we need to prove the same thing. We need to change the form of the set difference A minus B to A, the intersection of set A and the complement of B. It's the same thing as A minus B equals to A and the complement of B. So firstly, we change the form, the intersection of set A and the complement of B, minus B and C complement. And again, we change the form, so it's A and B and E and C complement, then a complement. And also we have a complement outside. And then we take a complement inside. We have a big complement outside, and then it's B complement, and then the intersection will become a union, and then the double complement is itself. Okay. As for the underlying part, we can just got the complement of B. And then a key point, De Morgan law again, complement of A or B. And we found this is right hand side. For question 15, we need to prove a statement by showing that each side of the equation is a subset of the other. So the method is fixed. So we need to show the left hand side is a subset of the right hand side, but it's only one hand. We also need to show the right hand side is a subset of the left hand side. The method is fixed, and then for the two aspects, it's almost the same. So we prove the left hand side is a subset of the right hand side. So for any x is in the set A or B, and the complement of the intersection A and B. This means x is in A or B, but not in the set A and B. And then we can use distributive law, such as x is in A or B. So x can be in A and also can be in B. X in A and x is not in A and B. Or x is in B and x is not in A and B. So according to the definition, x is in A, but x is not in A and B. It's A minus B, right? That's the difference. So we have x is in B and x is not in A and B. It's B minus A. Okay, x is in this set. So that's all for question 15. For question 16, it uses A delta B to denote the symmetric difference of A and B. It's the set containing the elements in either A and B, but not in both A and B. We can use a Venn diagram to denote the relationship. So it's in A or B, but need to remove the intersection out. So from the Venn diagram, we can know the left side is A minus B, and the right side is B minus A. So it also can be A minus B or B minus A. And also we need to recall A minus B is what? Is A and the complement of B, or B and the complement of A, right? So for the first question, we need to prove A delta B equals to A by showing that each side of the equation is a subset of the other. The first thing is that we need to change the data symbol into what we are familiar with or with our common use by using a definition. So first thing is that replace the data symbol using the underlined part. So let's replace the first data. We will have A and the complement B, or B and the complement of A. And then we have a second data. So here we can denote this as C. So we will have C and the complement of B, or B and the complement of C. So for this part, firstly we need to calculate the complement of C. Okay, so let's do it here. The complement of C is A and the complement of B, or B and the complement of A, and then the complement. Okay, it's just like a negation, so we need to take the complement inside. Firstly, we need to take a negation of the first part, and then change the union into intersection, and then the complement, right? It's just like negation, and then we take negation inside for the first part. It will become a complement of A or B, and a complement of B union A. And then that's complement of set C. Okay, and then we need to take the concrete expression of C into C here. So we can denote inside C we have a OR operator to connect the two, and we have and outside, so we can use distributive law. A and B and the complement of B, or the second part, sorry, the complement of A and complement of B. That's for the underlying part, and also we need to union B and take the underlying part into the complement of set C. Okay, and we can note and the complement B and complement B is also the A and complement of B. Or we can see there is a B here and a complement of B. That's a empty set. Or we can see we have an and here, so we can just calculate in sequence. And for the first and, we can see there is a or inside, so we need to use a distributive law. We will have B and the complement of A, or B and B, and then and the complement of B or A. So we can notice that, so B and B is a B here, right? And then B or B and a complement of A, you can think in this way. B and the complement of A is the result is a subset of B, right? And the union B, a part of B or the whole B, the result would be B, right? So the underlined part would be B. So the second part would be B and the complement of B or A. Also, again, we can use distributive law, so it's B and the complement of B or B and A. So for the underlying part will be empty set. So the whole thing will become A and the complement of B, union empty set, we can omit it, and again we have a union, this is also empty, or B and A. So the result will become A and a complement of B, or A and B. We can notice there is a A in common, so we can use the inverse distributive law. We take the A outside and the complement of B or B. When we reach here, we can check can this line and this line are consistent or not. So for this, we can just use a distributive law. We will have A and the complement of B, or A and B. Okay, we can see they are the same, so this expression is correct. So B, the complement of B or B is always the whole set, the union, the whole set, the universe. Okay, so A and the universe would become A. So as for the question 1, it's a little bit long. And then for the second part, we need to use the membership table to prove A delta B, and then delta B equals to A. So for using a membership table, we need to include all the corresponding set in each column. So we will have A here, B here, and then we have A delta B, right? And then the second delta B. If the whole column is the same, then the two sets are identical. We can see, actually we can just treat it as a choose table. And then we need to calculate A delta B on the specific A and B. A and B equals to what? The white part. Okay, so it's A minus B unites B minus A. So when A is empty, B is empty, A delta B is also empty, and again also the same. So if A is empty, B is 1 here. So A minus B will become empty. B minus A will be 1, so it's 1. And again, we can calculate A delta B, it will become 0. So similar for all the values will become 1, 0, 1, 1, and 1, 1, 0, 1. After the calculation for the membership table, we can see the column A and column A delta B and then delta B shares the exact same values, 0, 0, 1, 1, 0, 0, 1, 1. So we say the two sets are equal. For question 17, we can use a Venn graph to show the relationship between the different sets. So the universe is 200 students, and 88 choose to endurance, so we use D to denote the group of the students choose to endurance, and the same for the mango, we use M, and then for the lychees we use L, and then the cardinality of the set is the number of the students who choose to eat the corresponding fruit, such as the cardinality of D is 88, since there are 88 students choose to eat durians. So the same for the cardinality of M, it's 73. The cardinality of lychees is 46. So we have 3 sets. D, M, L. Okay. 34 of them had eaten both durians and mangoes. Durians and mangoes. So the cardinality of the intersection of durians and mangoes is 34, and similar for remaining case is that eat durian and lychees is 16, eat mangoes and lychees is 12, and then eat durian and mango and lychees is 5. Okay, and the question is that how many of the students ate none of the 3 fruit? So it will become the complement, the complement, and the complement. It equals to what? And how many of them only ate mangoes is that? So for the first question, we can just start from this. The whole students is 200, and then we have 3 group, and the some of the group are intersected, right? So this would become the negation or the complement of D or M or L. So this problem become calculate the universe minus D or M or L. Okay, and then D or M or L, the cardinality would become, we calculate D, M, and L first, and then remove the repeated part. After remove the repeated part, we need to add actually how to start from here to here. There is a formula. Okay, we have learned in the previous chapter. So actually we have all elements in the right hand side, so we can just take the numbers into the symbol. We have 150, but we only calculate who eat fruits. Okay, but the question is to calculate the students who ate none of them. So we still need to do, we have 150 here and then 200 here, so the results will become 50. For the second question, we need to calculate the students who only ate mangoes. So using a Venn graph, we have mangoes, durians, and lychees. Only eat mangoes means we need to calculate this part. Okay, so it's eat mangoes but not eat durians, not eat lychees, carnati. Will become, first we have the students who eat mangoes, but we need to remove the students who eat mangoes and durians. Also, it's this part. Okay, and also the same for the mangoes and the lychees. We need to remove this part. After remove the two parts, we can find the intersection of the three group. We remove them twice, so we need to add them back. Okay, eat mangoes and lychees. After remove the two parts, we have shown we remove here. Actually, is that we remove here, and then we remove here. So in the intersection of the three group here, we remove it twice, so we need to add back the intersection of the three group. And then we take the concrete number into these symbols. So we have 33 students eat mangoes, and then 34 ate mangoes and durians, and 12 students ate mangoes and lychees, and 5 students ate all the three fruits. So we will have 32 in the end. For question 18, we need to prove or disprove the Cartesian product of set A and set B minus C equals to the Cartesian product of A and B minus the Cartesian product of set A and set C. For this kind of problem, we usually start from the definition. So the Cartesian product will have an ordered pair. So we have an ordered pair x1, x2, and x1 is in set A, x2 is in set B minus C. B minus C here means x2 is in set B and x2 is not in set C. So for this case, we can just have x1 chosen from set A, x2 chosen from set B first, and then remove the situation that didn't satisfy. So we will have x1 chosen from A, x2 chosen from B. Okay, and then remove x1 chosen from A, x2 chosen from C. For the first case, it's a collision product of A and B. So it's x1, x2 chosen from. We need to remove. So what I mean, and x1, x2 didn't belong to A times C. Again, if we treat this as a C or other, we use Mn, okay, Mn here. Exist M and is not in another set N. This means M minus N. Right. So M here is A times B minus A times C. That's right hand side. That's all for question 18. Thank you all.